Okay, it's been a while.
Yeah, it has been a while. I think that I've been doing pretty good with this unit. It's just that I have the test on Wednesday, and so I figured that we could just go over like one or two problems from each of the mini units.
Sounds good. I'll let you pick the problems. You tell me, pick the ones you are not certain of. In other words, don't give me the ones you know how to do. Give me the ones you're not sure how to do.
Okay. So this is for chapter 9 out of it, and so it's on like function or the rational functions and like joint variation and stuff like that.
Did I open the book? Let's see. We have the same book, but I don't remember if we have the same exact book. Do you have some exercises from the book?
Yeah, it's the chapter 9 review. For me, it's on page 576.
576?
Yep.
Okay, yeah, that's where my chapter review for chapter 9 begins. Which ones you want to start with?
All right. Can we just start with one from 9.1 with the joint variation? I'm pretty good with the inverse, but sometimes with the jointly I get...
Okay, so we want to start with number 5 then.
Yeah.
Okay. So we've got, well, let's first of all talk about their definition. How can I write z varies jointly with x and y?
So would that be z equals kxy?
Yep. There's always a k there. And jointly just means that they're being multiplied. They're not being divided, as opposed to inversely. Okay.
All right.
If I didn't have a y, then z would vary directly with x. And if y was in the denominator, z would vary inversely with x and y. But for z to vary jointly with x and y, then the k is k times x times y. And now they always give you enough information that you can calculate k. So what's the next step?
So then since x equals 1, y equals 12, and z equals 4, you would plug in those three to figure out what k is?
Correct, always. The first step is always going to be to figure out what k is. So what's k?
K is, let's see here, 48 equals 4, so then divide both sides by 48.
Hold on.
Oh, no, 12, 4. Sorry.
So this is equal to 12k. So we got 4 equals 12k. What's k equal to?
K equals 1/3.
All right. Now we have a specific equation for this particular model. In other words, this is our equation. Okay? So whatever they're going to ask, they're going to give you two of these three variables and want you to answer the other. So they say, find z when x is 5 and y is -6. So tell me the next line.
So then it would be z equals -30/3.
Plug it in. I prefer plugging it in than having you do 2 or 3 steps at once.
Okay.
Just because I can follow what you're doing.
Yeah, all right.
If you jump ahead of me, I can't tell really where you've jumped to.
Yeah.
Okay, and that is -30/3, which is -10. So that's the answer. Find z when x is 5 and y is -6. Now, for 6 and 7, they give you different x, y, and z, but the general equation is always that.
Okay.
It's just a question of calculating a different k. So, yeah. So what's k here?
K
Well, do it step by step.
in 6?
Well, you got to, in other words, on number 6, yeah, they're giving you an x, a y, and a z, and that's going to allow you to calculate k.
Yep. Okay, so then it would be the z equals kxy, and then plugging it in, you would have -6 equals k, and then times 8 times 6, and then that would be -6 equals k, oh, 48k.
Make sure you divide.
Okay.
In other words,
So then,
k is equal to -6 divided by 48, or 6 times 8, right?
all right.
Now I can cancel the 6's, and I get k equals what?
1/8.
-1/8.
Yeah, -1/8.
Okay, so now I have a general, or excuse me, now I have a specific equation that applies. In other words, I've figured out what my k is, and there's my equation for this model. Now,
Okay.
find z when x is 5 and y is -6.
All right. So then z equals -1/8 times 5 times -6.
All right, I'm going to trust you know how to do that.
Yeah.
All right. We need to do 7, or shall we go on?
I think we can move on from there. I'm pretty
All
good
right.
with it.
Yeah, once you get the hang of those direct, inverse, and joint relationships, the method is the same every time. The very first step is always to figure out what k is. And then once you have k, then you can handle whatever x and y they throw at you.
All right.
All right, what next? Which problem?
Graphing simple rational functions. I've been having a bit of trouble with just graphing them, I guess.
Let's look at number 8.
All right. So y equals 3.
Now, I think it's important to recognize that this is hyperbolic in nature.
Okay.
Okay, what's the parent function?
Y equals k over x.
Well, 1 over x.
1 over x.
Yeah, and I'll explain further. Now, 1 over x is a elementary function. That is one of your 10 basic elementary functions. You always want to know how this graphs. This is your basic hyperbolic function, and it has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0, and it looks like your standard hyperbolic function looks like that. So if we know how the parent function looks, now how does that differ? How does 3 over x minus 5 differ from our parent function?
Does it stretch it by 3 and then move it to the right 5?
Correct. It vertically stretches it by 3, and this minus 5 being part of the function means we're going to horizontally shift it by 5. Well, when you have a vertical asymptote, and I'm going to shift it by 5, that vertical asymptote goes over to there.
Okay.
Does not change the horizontal asymptote. there is no vertical shift. So the horizontal asymptote stays the same. Okay? And now if I want to graph it, the secret to graphing hyperbolic functions is to draw your grid. And the green represents our grid. Okay, so I know how it's going to look. It's going to look like that and like that.
All right.
Easy as that. Now, the vertical stretch by a factor of 3 perhaps makes it look a little bit more like that and that. It's still going to be asymptotic to my green dotted grid. But notice the blue line is stretched a little bit versus the green line. In other words, every point that's on the green line would be 3 times further away from the x-axis, right? That's what a vertical stretch means. And below the x-axis, every point on the green, well, the blue is going to be 3 times further away from the x-axis. So I haven't actually drawn it very good. My blue is maybe a vertical stretch factor of 2, but you get the idea, I think.
Mm-hmm.
The key thing isn't so much the vertical stretch factor, it's what it did to the asymptotes. Okay?
Okay.
They want 3 things here. They want you to graph it, and they want you to state the domain and range. What's the domain?
Is the domain all real numbers not equal to 5?
Good. What's the range?
All real numbers except 0?
Except y not equal to 0.
Okay.
Notice that it's y. X can be 0. In my blue line, x is 0 right there.
Okay.
Okay? But y is never 0. In other words, y never crosses this horizontal asymptote at y equals 0.
Okay.
Okay, and that's all they asked. So let's do one more of those at least.
All right.
Y equals 1 over x plus 4 plus 2. Again, hyperbolic in nature. The x is in the denominator. In fact, whenever the x is in the denominator, it tends to be hyperbolic. If I had this, that's hyperbolic. That is going to look just like my hyperbolas. It'll look a little different. In other words, the vertical asymptote will change, the horizontal asymptote will change, but it's hyperbolic in nature. In other words, it's going to look hyperbolic. Well, just like this.
All right.
What's the consequence? And the very first thing you want to do when you draw hyperbolic functions is graph their grid.
Okay.
Where is my vertical asymptote going to end up being?
The vertical asymptote is at x equals -4.
Good. Draw it. Where's my horizontal asymptote? Where would the horizontal asymptote of just that part be?
Y equals 0.
Okay, now what's the consequence of that plus 2?
It moves it up 2. So y equals 2.
And that does affect the horizontal asymptote. In other words, the horizontal asymptote is now at 2. Y equal 2. So now that I have my grid on there, it's pretty easy to graph. Just graph a hyperbolic function on that grid.
All right.
What's the domain?
All real numbers that x doesn't equal -4.
And the range?
All real numbers y doesn't equal 2.
Good. I think you got that. Let's go on. Well,
All right.
hold on. Before we go on, 10 and 11.
They both have x's in the numerator too.
Let's do let's do 11.
Okay.
And the only reason I want to make sure we do 11 is because it's quite a bit different looking. Where is the new vertical asymptote?
Is it at
In other words, it's not exactly obvious that this is going to be a hyperbola, right? In other words, this doesn't really look like the previous two, but it is a hyperbola, trust me.
Okay.
In other words, even if you have x in the numerator and x in the denominator, it tends to be hyperbolic in nature. So the first thing we got to do is to draw a grid. Now, we need our vertical asymptote and our horizontal asymptote. To get the vertical asymptote, figure out what makes the denominator 0.
So then it would be 1?
Yeah, x equal 1. So that's our vertical asymptote. We know you can never divide by 0. That's what makes vertical asymptotes, is division by 0. Okay. Now the horizontal asymptote's a little tougher. Do you know what it is here?
Is it 2?
Yeah. Because it's the ratio of the coefficients. And that's always the horizontal asymptote if the degree of x is the same in the numerator as it is the denominator, then the horizontal asymptote is the ratio of those coefficients.
Okay.
If the degree is greater in the denominator, like that, than the numerator, then the horizontal asymptote is always y equals 0.
Okay.
That's why when we had y equal 1 over x, well, the denominator is bigger than the numerator, right? That's a 1. And the numerator is basically x to the 0. So that's why we had a horizontal asymptote at y equals 0. But here, and you always take the highest degree polynomial in the numerator, which is 2x, and in the denominator it's x, so the ratio of those coefficients is 2 to 1. Now we have our grid. Now we can graph it.
All right. And then would it just be a regular graph?
Well, almost. By almost, sometimes this is first and third quadrant of our grid. Sometimes it's second and fourth, depending on whether there's a negative sign somewhere. Usually it's first and third, like I've drawn it. How can we tell? In other words, what is one very easy way to tell whether I've drawn it correctly?
Is it to plug in a point?
Which point?
I don't know.
How about any value of x that's to the right of our vertical asymptote? Well, our vertical asymptote's at 1. Let's plug in 2. When you plug in 2 for x, what is y equal to?
4 plus 5 over 2 minus 1. So y equals 9?
Yeah, and that is certainly above my horizontal green asymptote, correct?
Right.
That tells me I've done it correctly. In other
Okay.
words, if it ended up down here, then I would know my answer was in second and fourth, not first and third.
All right.
And you might get that from something that looked like this, minus x plus 1 over x minus 1. That's probably going to be in second and fourth, not first and third.
All right.
Okay? I'm not real good at looking at the function and telling whether it's first and third or second and fourth. But it's real easy to figure out by just plugging in a value. You could also plug in 0 for x, which actually makes it a little bit easier, right? In other words, if I plug in 0 for x, then I get minus 5. Well, if I go to the 0 for x, yeah, I haven't drawn it quite right. In other words, instead of drawing it like that, I should have drawn it like this. And now, 0 for x gives you minus 5. It's clearly not second and fourth. In other words, second and fourth would look like that, right?
Right.
Well, 0 for x clearly does not give you a positive number greater than 2. So all you have to do is plug in a number to tell whether you're in first and third or second and fourth. That's really the easy way to do it.
All right.
On number 11, what's the vertical asymptote?
X equals 1.
It's the horizontal asymptote.
Y equals 2.
All right, let's go on.
All right.
Let's look at number 12.
What?
Now, if I have in their example, let me use their example. The one thing you notice here is it's still hyperbolic in nature. In other words, I still have an x in the numerator and an x in the denominator, but the power in the numerator is 1 greater than the denominator. Well, the only way to figure this problem out is to go ahead and do that division. In other words, you got to do this. And you got to leave room for dummy variables, like that.
Okay.
And what you get when the numerator is exactly 1 degree higher than the denominator is you get what is called an oblique asymptote or a slant asymptote. And if you look at their picture in the middle of that page, you can see that there's a vertical asymptote, but there's also an oblique asymptote.
Yeah.
Well, the equation of the oblique asymptote is what you get when you do this division. Can you still hear me? I just got, okay, I got a little message saying my audio connection had been lost temporarily, but then it immediately came up and said it had been restored.
All right.
All right.
I can hear you.
Do you know how to do this long division?
I don't.
Make sure you do.
Okay.
It's not hard. You take this term here and divide it into that term as your first step, no matter what else is there. What's x divided into 3x squared?
Is it just 3x?
Now you take that 3x and you multiply it by both terms.
Okay.
And like all long division, you then subtract. So I had to have that dummy variable there so that I could do this. So I get 0x minus 6x is minus 6x. Bring down the 0 and repeat.
Okay, so then that would be minus 6.
Yeah, and that's the equation of the oblique asymptote. That's all you need to do. You don't need to go any further. You don't even need the remainder. Notice that if I do multiply the minus 6 times both of these, I get minus 6x minus 12. And now I get a remainder of 12, so I could say there's a remainder of 12 over x plus 2, which is all fine and good, and that's true, but doesn't do anything towards graphing it. If I want to graph this thing, where's my vertical asymptote?
-2? Or would it be at 0?
No, the vertical asymptote comes from whatever makes that 0, which is -2 for x.
Okay.
In other words, the one value that x can never have is -2.
All right.
Now, I've got to graph that 3x minus 6. Well, I know that that goes through -6. Got a slope of 3. So the slant asymptote looks like that.
Okay.
The graph looks, you know, it's going to look something like that. Hold on, I need the other part of it. In other words, I didn't draw it fully enough. The asymptotes go to infinity. And the rest of the graph looks like that. Okay, so whenever you have slant asymptotes, much harder problem. First of all, you have to do the long division to figure out the equation of this slant asymptote. It's always a straight line, incidentally. Just like vertical asymptotes and horizontal asymptotes, they're always straight lines. The difference is that from my graph, I actually have no idea what that point is on the y-axis, or this point. So I can do domain easy enough. What's domain? Hold on a second. I'll bet they don't ask for that. No, they don't. There's a reason they don't. So all they ask you to do is graph the function. Well, I graphed the one that they had in the example, but notice that I have no idea what this y value is right there. So if they wanted to know the range, I'd be out of luck. I know the domain is all real numbers except x equal -2, correct?
Right.
But the range is -infinity to that plus that to positive infinity. But what is this value? Well, the only way I can really tell, put it into my calculator, put a trace on it, and figure out the maximums and the minimums. Then I would know what those y values were, and I would be able to give you the range. But without a calculator, without a graphing calculator, there's no way to tell what this point is right there on the y-axis, or the x-axis for that matter. So I don't have any idea what that point is. I might know the general shape of the graph, but I don't know the specific low point or high point. And that's why they didn't ask for the domain and range here. It's because in order to give the domain and range, you would have to have a graphing calculator.
All right.
Now, look at 13, just because it looks kind of interesting. Y is x cubed over 10. They just want you to graph it. What's the parent function?
Is it still y equals 1 over x?
Just a second. Wow, I lost my ability to get black coloring. Funny. Yeah, I mean, I get gray is all I've got. And if I pull up colors, it doesn't even give me a black on the colors. It gives me grays only. All right, we'll live with gray. Parent function here is y equals x cubed.
Okay.
It's a really good idea to always know the 10 basic elementary functions, what their graphs look like. This graph looks like that. That's y equal x cubed.
Okay.
How does this function differ?
Is it not a stretch, but almost a shrink of 10?
By how much?
10?
Yeah, in other words, I can rewrite this as y equal 1/10 x cubed. Same thing, right?
Mm-hmm.
Now the 1/10 is a multiplier, and since it's less than 1, it's a shrink. It's not a stretch, it's a shrink. And shrinks look, in other words, every point that's currently on my gray curve would be 10 times closer. So it's going to look something like that. In other words, a lot flatter. I'm trying to make that point right there be 10 times closer to the x-axis as the point on the black curve.
Okay.
Same thing over here. That point right there should be 10 times closer than that point because it's a vertical shrink by a factor of 10. Stretches mean it would be, in other words, if it was 10x cubed, then every point would be 10 times further away. But since it's 1/10, every point is closer, which makes it flatter.
Yeah.
Now I get my black back. Yeah. What the heck happened there? That was weird. All right. Let's see. What else we got here? I don't think we want to do, let's go to number 16.
All right.
These are very common. You're going to get a lot of these kind of problems. So
Okay.
make sure that we know how to do them. These are always factoring problems.
Okay.
In other words, what you never want to do here is multiply the numerators out. You'll notice that if you FOILed the numerators, you would end up with an x to the 4th, and the whole problem would just become more and more complicated. So let's look at this numerator, factor it. Let's look at this denominator, factor it, and let's look at this multiplier numerator, factor it. So let's start in the upper left, factor that.
Okay. So then,
What do you get?
would it be x plus 3, x minus 3?
When you're factoring something, when you're done, always multiply it back together again to make sure you get what you started with. Notice that had I put x plus 3, when I multiply it back together again, I do not get x squared minus 3x. The only way I get x squared minus 3x is if it's x times x minus 3.
Okay.
Now, take the greatest common factor out of the denominator. What do you get?
All right. Would that be 4x times x minus 2?
And now factor this term right there. There's no greatest common factor, but the second factoring technique that you should always look for, when you're looking to factor, always to go in this order. Go greatest common factor first. I could take a 4 out, but that doesn't help. But difference of perfect squares is what you should look for next.
Okay.
This is difference of perfect squares. What is it?
That 2x plus 4, 2x minus 4?
Yeah, 2x plus 4, 2x minus 4. And I actually could take a 2 out of one of these. In other words, I can still take a greatest common factor. Let me do it. Because what that leaves is x minus 2. And now I can do a lot of canceling. In other words, I can cancel that x minus 2 with that x minus 2.
Yep.
I can cancel this 2 with that 4 and turn it into a 2.
Okay.
And what does that leave me? That leaves me x times x minus 3 times 2x plus 4 in the numerator, and in the denominator the only thing I have left is 2x. Well, I can cancel that x with that x. And so my final answer is x minus 3 times 2x plus 4 all over 2. I can even take another 2 out of this. Turning
out of the
1 and 2, and then canceling the 2's. So now I end up with x minus 3 times x plus 2. And that's my final answer. And you don't need to multiply those two together. Actually, factored answers are better than answers that are multiplied out.
All right.
They just are. And the reason is that you never know what you have to do to an answer. Maybe we're going to divide this answer by x plus 2, and so it's much better in factored form than it is in quadratic form. If I multiplied these two together, I'd have a quadratic. Either one is the correct answer. It's just don't worry about multiplying factors back together again. You don't need to do it. Okay? But this is an extremely common problem, so let's do one more. Let's do number 17. 5x divided by 1 over x minus 6 times x squared minus 9 all over x.
Okay.
So first of all, how do I do division?
Well, with division, wouldn't it be in the better form right now, like as it is, because that way you have everything on one level instead of having to do with multiple fractions?
Well, we never do division. We always do we always turn all division problems into multiplication problems.
So you would take the opposite reciprocal?
Yeah, so I flip and multiply. So this is my first step. and then I multiply, and now factor that numerator. If something can be factored, factor it, always. X squared minus 9 factors how?
X plus 3x minus 3.
And I still have the x down there. Okay, now I got all multiplication going on. So I can do some canceling. I can cancel that x with that x. And when I say cancel, I mean replace with the number 1, not the number 0. Okay? So now it looks like my final answer is this. And I can't do much with that answer. I could multiply all three of those linear terms together, but that just turns it into a cubic. And like I said, you're better off leaving everything in factored. If they gave you the answers in the book, this would be your answer, not the cubic that you would get after multiplying everything together.
Okay. Cool.
Okay, let's see. We got 15 minutes here. Number 18, similar kind of problem. Let's do 18.
All right.
So what's the first thing? Without factoring, what am I going to do? First of all, turn it into a multiplication problem.
Yep, so take
Always turn your division problems into multiplication problems for these kind of type problems.
Okay.
So it's multiplied by what?
X squared over x squared plus x minus 12.
Now we got this minus 1 out there. Well, that minus 1, we'll leave that out there. Let's deal with this for the moment. What's our next step?
Then you would factor?
Okay. Upper left numerator factors into what?
X minus 3x plus 2? Or x plus 1, sorry.
Good. There's the x plus 1. You can usually be fairly certain that some of these are going to cancel out. So it's not surprising that x plus 1 would be one of the factors. Okay. This, well, I could make that x times x. Okay, I will. That's the numerator. Factor the denominator.
X plus 4x minus 3.
Good. You're good at factoring. I like that. And now cancel everywhere you can cancel. Well, I can cancel that with that. I can cancel that with that. Now what have I left? This leaves 1 and 1. So I'm left with x squared over x plus 4. And that's my final answer. I cannot simplify that anymore.
All right. And then just plug in my...
Yeah, let's talk about that for a second, because I think a lot of students are a little confused by this. If I have a plus b over c, I can separate that into a over c plus b over c. But if I had a over b plus c, that does not separate into that fraction and that fraction. The only time I can split it into two fractions is if my denominator is a single term. If the denominator is a binomial, I cannot split it up.
All right.
Okay. And you'll notice that in this last problem, if I can find it, well, we had a binomial term in the denominator. And so we couldn't really do anything more with it. We had x squared over x plus 4, I think. Well, that's as simplified as you're getting. There's no way to simplify that. It's definitely not x squared over x plus x squared over 4. In other words, that's what I was trying to point out.
Okay.
Oh, this was our answer, and I forgot there's still a -1 there.
Yep.
So this would actually be my final answer. I wouldn't really have to go any further than that. I don't think I would. No. Yeah. All right. Let me turn the page and see what else we got here that we can. All right. These are always key. Let's do number. First of all, let's do number 20.
Okay.
Actually, a little easier than 19.
All right.
Then we'll do 19. When I'm adding or subtracting fractions, very first thing I got to do is come up with a least common denominator. Well, what is my least common denominator?
Is it x squared minus 25?
You know what? I actually think it works better if you leave it unmultiplied.
Okay.
I'll show you why. That's my least common denominator. You got it. It's just that I would rather write it like this. And here's why. What goes here?
X plus 5. So you could cancel it out.
Notice that whatever goes there has to equal what I started with. Well, if I write x plus 5 times x plus 5, I can easily see that it does equal this. In other words, I'm trying to make that fraction equal that. Well, when I write it completely in factored form, I can tell that that would cross with that, and I would end up where I started with. And that's the advantage of writing the denominator in factored form rather than multiplying it out, because then you can tell that you haven't made a mistake.
All right.
What goes over here on the right numerator?
3 times x minus 5?
Yeah, and use liberal use of parentheses there. And I can instantly tell that this is the same because that x minus 5 would cancel with that x minus 5, and I would have what I started with.
Yep.
Okay. So now I'm still going to leave my denominator in factored form because who knows what I'll end up with in the numerator. Maybe I'll get an x plus 5 or an x minus 5 that I could cancel. Well, all right. Next step is what?
The next step is to subtract the two numerators, right?
Yeah, exactly. But before we can do that, you need to distribute the 3.
Okay.
In other words, let's go ahead and we'll multiply. Yeah, I think we need to multiply this together because we might be able to simplify it. You'll see that we can. So that's these two multiplied together. And then I'm going to subtract. What's the rest of it?
Minus 3x minus 15?
It's not minus 15 anymore.
Plus 15.
You see why? Because this minus sign has to be distributed to every term. And the two minus signs turn into a plus. So it becomes plus 15. And now I can definitely simplify the numerator. What's the numerator now become?
X squared plus 7x plus 40?
Yeah, all over x minus 5 times x plus 5. Now, occasionally, if I go ahead and factor the numerator, I might be able to find two factors where one of them would be what's in the denominator, and I'd be able to cancel it. But
Okay.
in this case, I can't. In other words, there are no factors of 40, and if I check the two factors that are closest together, they would be 8 and 5, right?
Right.
But 8 and 5 don't add to 7.
Nope.
So I immediately know that I cannot factor this numerator without using the quadratic formula. And if I have to use the quadratic formula, I'm certainly not going to come up with a linear factor like it's in the denominator. So I'm not going to be able to cancel anything out for sure. Therefore, don't factor it.
Okay.
Only factor that is if you can come up with a factor that might cancel with one of these denominators. And clearly I can't do it. So leave it exactly as it is, and that's your answer.
All right. Cool.
Okay. Let's do 19 now.
Okay.
Just about enough time to do one more here.
Cool.
Now this is a little different. That's why I wanted to do the other one first.
Okay. So
What is my least common denominator?
x squared times x minus 2.
Good. In other words, it's not always the product. In other words, if I multiply these two denominators, I get x minus 2 squared. But I don't need to square it. In other words, this is the least common denominator. And by that, I mean that both terms divide evenly into that. If I divide this least common denominator by x minus 2, I get x squared. If I divide it by x squared times x minus 2, I get 1. So I don't need to go any higher than this. So the upper left is still that. What's the upper right if that's the least common denominator?
X times x squared, so x cubed.
Yeah. And notice how easy it is to check to make sure you haven't changed it. By leaving the bottom factored as opposed to multiplied together, it makes it far easier to check your work, to make sure that this is the same as this. And that's the key mistake that I could make if I'm going to make a mistake. By doing it this way, you are going to eliminate a lot of possible mistakes. So let's see, what's the final answer?
And then x cubed plus 5 over x squared times x minus 2.
Yeah, and leave it just exactly like that. Now, I'm going to just cover one thing that you might not know. Obviously, if I have things like this, I can cancel, right?
Right.
In other words, you can always cancel whenever anything is identical. Well, there's one other situation where you can also cancel, and that's that. In other words, what is x minus 3 divided by 3 minus x? That's always minus 1.
Okay.
Okay? That's the only thing you ever need to look for. In other words, if they're not identical, you're done. But occasionally, even though they're not identical, you can still cancel it. Notice why x minus 3 over 3 minus x, that's the same as x minus 3 over minus x minus 3. Notice that minus x minus 3 is the same as 3 minus x. And
Yep.
that clearly is minus 1, right?
Yeah.
That's why this is minus 1.
Okay.
So whenever you see an a minus b over a b minus a, that's minus 1. And that's the only thing that I can think of where you can cancel without them being identical.
All right.
You can't, if I had x minus 2 all over minus x plus 2,
Would that work?
no, wouldn't. Can't do anything with that. Ah, yes, excuse me. Yeah, because that's x minus 2 over 2 minus x, so that is equal to minus 1.
Okay.
Yeah. All right. Morgan, I'm going to let you go. I hope I've helped. We didn't quite get through the last set. I wish we could have done some of the 20 through to 25. That's just hard algebra, but it's not doable. I would expect you can do all of those, 22 through 25.
Yeah. I was pretty good at those, so I think I'm pretty comfortable with them.
It's finding a common denominator, no matter how complex it is. In other words, even if somebody gave me a problem like 1 minus 1 over x all over 2 minus 3 over x plus 4 minus 7 over x, you can make this as complicated as you want and have as many levels as you want. And the secret to all of them is find a common denominator, turn that into a single rational quotient. Same thing with that, same thing with that.
Okay.
Okay?
Cool.
That's all that 22 through 31 are really all about, is finding common denominators, factoring, canceling where you can, stuff like that.
All right. Awesome. Thank you so much.
You're welcome. Have a good luck on your test, and I will talk to you next time.
All right. Thank you.